title is a Smart Textile Integrated Wearable System. So in my presentation, I'm going to cover a number of issues. First, to talk about our motivation, and then we will talk about the devices we produce in research and development, and also important issue of integration of soft and hard rigid microelectronics and integration problems, and then probably briefly talk about its applications, and that's outline. So maybe first let me to say what is smart textiles. That is textiles made of fiber assemblies. These assemblies have a capacitor of sensing, actuating, adapting, communication, and self-healing, self-powering, memorizing, living functions. In other words, they are like living things. It's a total system. Okay, and a feature of these smart textiles are they have interactions or reactions upon external stimuli or by pre-programming. And because of advance of nanotechnologies and in material science and technology, and now it's quite feasible to impart submicron or nanometer scale structure on the surface or inside the fiber to impart this function, which will never be realized before. Why is the textile such a nice platform for achieving smartness? And what are the features they are? They are highly flexible, and normally they can have a very large deformation in many repeated cycles. They are lightweight, and normally their area is bigger than millimeter square, compared with microelectronics. And they rent themselves for large-scale industrial application. Okay, and at the same time, they can be made into clothing that need to be fashionable and comfortable. And these kind of wearable items can be put on real-time application on human beings and other moving machines and animals. The whole thing is a new interactive technology. It wasn't there before. Now we have about 20-some years history of intensive research. Unfortunately, working in this era, therefore, we have, looking back, we have a number of things already being used by industry. Maybe I just briefly to say something. One is the fabric sensors. One example is a strand sensor. Textiles, because of a fibrous structure, they can be deformed in large extent. Normally, the strand level is around 100% or something, and fully discovery is expected. Therefore, this can be used for strand sensor. That means to measure the strand or deformation in large scale. Now, a typical example we developed is a fabric, a knitted fabric, which is elastic, can fully recover from many repeat cycles, coated with a layer of conductive composites, and then connected in electricity. Such kind of sensor, it has a very good response in its resistance, relative change in resistance, conductivity, inverse proportion, right? And against the strand, this curve is almost linear in many cycles. Okay, up to, in this case, 60% still repeatable. And this fabric sensor has a very nice response in composite status. And a relative change in the resistance is almost linearly proportionally to the strand level. And the temperature is not that sensitive. And if the change in temperature is less than 10 degrees C, and we probably don't need a compensation. Therefore, it rents itself to be very good wearable sensors. And people may ask, what is the effect of moisture? Has no effect. Okay, so this is a quasi-static. And also it has a very nice dynamic response. This the picture here on the right side, this part, it says the strain rate effect spanning several decades. And you can see is the response is almost linear. This calibration curve can give us very good application in anything involve impact in dynamic situation. Now, that is sensor example has been used by industry, it's been commercially produced. Now I'm going to probably talk about some of our recent work. Further investigation, not on the sensing side, it's more on actuating. That means the textile structure needs to do something. The first example I like to show is something, a piece of fabric that can change its dimension or shape or its porosity and without connected to electrical wires. So it has to be wireless and ideally utilize energy from ambience rather than connect with a battery or so on. Now, and this is using a bimorpho structure with an isotropic bias-oriented PP film laminated on very thin conductive fabrics. And this manufacturing process is quite simple, straightforward. And this fabric can be made into several devices. And in plenary form, you can see it can be actuated by external field like a magnetic field, or by a thermal field heating, or by lighting, or just directly connected to electricity. So the shape can change, and also deformation change, exert certain force, create kind of a structure. Now, the pictures on the right side and up one is that you can see these when temperature increases, and these components, these film and the fabric, they have a large induced thermal strain. Okay, and the difference is very large. Therefore, it's bimorpho structure and cause this buckling or bending deformation of the fabric in a very thin fabric. Okay, and the curvature change, you can see this diagram here is a curvature plot against the temperature, and it almost have a linear relationship. The blue line is a prediction, and the red dots are experiment data. Now, using this piece of fabric, we can make a garment, or some, in this example I show here, is a flower on a garment. Underneath the flower, there's a large holes. Therefore, if it's when it's hot in the sun, and this flower curved up, and there's a large holes exposed, so therefore ventilation can be better. Ventilation can be achieved. Of course, you can make into finer structure and making smaller holes, and that's just one simple demonstration how this actuator is easily made and in large quantity in mass production. Now, that is a fabric actuator can have a large deformation, create a holes or change shape, but a reactive force is very small. And therefore, we need looking for a lot of application. We need a large energy density and a large reactive force. The current technology, one of them is use a curved monofilament fibers in like this. Okay. The problem of them is, one is they cannot, normally it's made of nylon fiber or low density PE fiber. And they are nice, have a large deformation, same time high energy and density, and also reactive force. However, they cannot work at a low temperature. They start from room temperature up to maybe 100 degrees maximum. Then they stop working. Okay. And the challenges here, one is we want to work at a low temperature and still have a very good active actuation behavior. Now, what we do is we're using a material engineering, use a bi-component fiber composite here. And with this composite, you can see is a PI fiber and embedded in a PDMS, a soft matrix. Now, the chosen materials actually is after consideration of the working temperature and stability and also their mechanical properties. And this fiber is made into a bundle fiber into a composites, one linear dimensional composites. Then they've been twisted, form a structure, buckled structure like this. And you can see the picture here. Start with a single bunch of fiber and making a composites and twist them, and a single fiber still visible there. Okay. And here, this diagram shows the response with the temperature. The actuator actually worked from -50 to 100 degrees. That is much wider than the previous actuator. And that you can see the change in the length we call tensile actuation actually is linear with the temperature and many cycles. Okay. Then this is nice, can work at a lower temperature and also quite high temperature. Compare with the previous work, this diagram shows that comparison. The purple one is ours because that's the only one can work at a lower temperature, -50 degrees C, okay, and up to 100 degrees. And it has reasonable actuation and also almost linear. This actuation curve is almost linear, so you can control that better. Because this is engineered composites, we actually can achieve something even more interesting. Now, this diagram here, this diagram here shows this very surprising behavior. It's called thermal hardening. And most composites, these composites is made of two polymers, right? One is the PI and polyimide. The other one is the PDMS. And these individual polymers, if you heat them up, they become softened instead of hardened. But put them together because the structure, because the internal stress actually behave thermal hardening. And this diagram shows this blue line on the top. When temperature increases, actually the modulus increases and the stiffness increases. And then that can give you exert more actuation power instead of softening. And this leads to application as some sort of massaging fiber or massaging, because when temperature gets higher, when you apply electricity to it, and instead of become softened and reduce the reactive force, the force actually increasing. We're trying to find out the mechanism and set up mechanical model for this analysis, and that gives us pretty reasonable prediction of the area and where this actuation hardening occur. Okay, now as I showed in the previous slides, all these smart textiles, they need energy, and most likely in wearable system using electrical energy. Therefore, we look at these, how we power these systems. That's a bottleneck problems. Okay, it's unsolved problem. Until now, we use a battery, right? Rechargeable battery. And now looking at electrical appliances, where the range of we are interested is from these micron watts to 100 milliwatts, maybe 1 watt, less than 1 watt. In this range, actually different devices will have different power requirement. So 1 watts probably is up, and micron watts is too small. Now, if we want to replace the battery or prolong the battery life, and in some very special situation, like people going to a remote area where you have no access of electricity, so probably most feasible source of energy is trying to harvesting energy from our surrounding and from ourselves. Therefore, we can look at mechanical energy from us and from surrounding, and looking at thermal energies, looking at radiation energies, and so on. Okay, so the next one, we concentrate on different kind of energy harvesters. And now, why we need to use fibrous structure to achieve this kind of situation? One is the application scenario. You need to be comfortable with people, right? And the second one, it does have a unique feature using fibrous structure. Now, this is some work we done that's 8 years ago, and we made 3 layer of fabrics. Okay, and they're all made of fabrics, and we have 2 electrodes and with conductive fibers in it, and 1 active fabrics made of a nanofiber non-woven structure that is electro spun by some piezoelectrical and also nanowires and embedded composite nanofibers. Okay, and we to make these electrodes, we're using silver coated fiber and wrapped on the elastomeric yarn. Now, look at the picture here, and on the output of this device compared with nowadays output is not that impressive. However, it does have an outstanding feature, and says why we need to use a fibrous structure instead of a fume structure. Okay, and now this is looking at the y-axis. That's the voltage the generator produced. Okay, and this x-axis is a number of deformation cycle. Up to 1 million cycle, the device still working. Okay, now if you compare with the thin film electrodes and other electrodes made of plates or metal foils, all printed thin film electrodes, and their life is normally thousands or 10,000s. Okay, and this can really go beyond 1 million and or even several millions. So that's a unique advantage of this harvester. Therefore, fibrous structure does have advantage in here. Then we followed on to generate more electricity power by using other means of conversion. For instance, one of them is triboelectric generator. This become quite a hot topic in the last couple of years because it's a relatively higher energy conversion efficiency. Okay, and now we have a question. Is we look at a lot of people working on this, and we also working on this found quite interesting behavior. But experiments doing it's quite time consuming, and without an engineering design based on scientific understanding, it's quite difficult to get it right, and also waste a lot of energy and time. Therefore, we do some modeling and trying to do theoretical analysis, and then trying to see whether we can establish engineering tool to guide the design and the experiments of these kind of devices. And here is our examples. And we have this contact mode and triboelectric and generator made of fabrics, active fabric electrodes, and active layers in the middle. And then nice thing is this model works. And the red dots are the experiment dots. And blue, you can see they almost spot on. Okay. And this nice thing about this model is it has no adjustment in any parameters. So all parameters are measured one and then put it in. So we have confidence this can guide us to answer a few questions. First, whether this device will work in one condition or continuous, and how many cycles, and what kind of optimal operation parameters, what are the optical material parameters, and what is the optical device structure, can guide us very quickly to the point. And most important thing to say, with this structure, with this material, with this operation condition, what is the maximum theoretical limit of this device can produce? Because we must know these upper limits, then we know how much we can improve, the improvement space, or whether it's possible or whether it's not possible to use this kind of device to achieve the target of power output. And we said it's below 1 watts, right, in milliwatts. And this is an important one. And from that theoretical analysis, we know the most important parameter in all the materials is charge density. That is a material specific. Now, in materials, people will ask, what kind of materials I should use? I use a thin filmed or a nano patterned structure, or I use a fabric. Which one is better? And we start to answer this question, compare with textiles. And the difference, these two mappings are mappings are really, the one is a film, solid structure. Their roughness in the order of microns. And then on the right side is a piece of fabric, knitted fabric. Their roughness in the order of millimeters. And you can see a large pore present in the fabric. And then when we do this measurement, we want to know, and because we're trying to determine the charge density due to triboelectrical actions, right? And the experiment setup is like the one in the top. We're using sliding mode. And the fabric is placed on conductive fabrics, conductive plates. Okay, and you will find interesting, charge density is not constant. Initially, the density is low. There are two materials. One is positive, the other one is negative. Okay, positive one is a PLA, polylactic acid fiber, and made of that fiber. The other one is a PTE, FE. And they increase the charge density, the absolute value increase, whether it's positive or negative, doesn't matter. They increase with time and reach a certain platform and the saturation stay there. Therefore, for these kind of triboelectrical materials, the behavior at the beginning is not constant, hasn't reached equilibrium. Therefore, a lot of people say that I use this as a sensor. I'm sorry, using as a sensor is not that good because the system is itself is changing. Okay, it's not reaching an equilibrium state. Only as they, after certain reactive distance, and they become. And the second one, and because this porous material and very soft, and roughness is in millimeter, and they change with pressure. And now, if we compress this fabric, okay, we can see the pressure level increase and effective contact area actually increase. Okay, because initially there's a lot of space in the middle, and they've been squeezed. And when they reach a certain plateau, reach a saturation where the materials is being compressed. Okay, that's to get a reliable measurement, we need that. And as the contact area increase, the surface charge per unit area, of course, will change. And then we need to find out, and in this fabric, which one is the best one. And we look at quite a lot of new fibers coming into play, and we construct a new extended Triboelectric series table from our experiments. Now, here I have two charge density. One is red, the other is blue, is black. The red one is the actual charge density, and after densification under certain pressure. The nominal one is because the contact area is small, and the nominal one is not stable, because when you change the pressure, that value increases. Normally, it's about half of the densified one. Okay, based on this, we have the new table and with all the charge densities. Now, next question. We know what material we can use. We can have a positive and negative. And people trying to use different kind of mechanism to see whether there's a synergy that can bring out more output. And we tried to look at these problems by stacking a dielectrical layer that is a triboelectrical one, and with piezoelectric layer. And then we analyze them, we identify in this kind of system, if you do not separate the output from two units using the rectifying circuit like this, you actually have a negative synergy. That means 1 + 1 is less than 2. And you don't have a positive one because there are some certain cancel out the phase difference between the output. So you do need two rectifying bridge to separate this unit. Then we can do the whole thing. So one needed to look at the output very carefully. Now, the mechanical energy, we have looked at enough of them. Another source is a thermal source. That is because a human being, when it's alive, their body temperature and the environment temperature must have a difference between them. Okay, utilizing this temperature difference, we probably can harvest certain amount of energy. Unlike the piezoelectrical and triboelectrical generators, they're working on periodical actions. Although the peak power output is higher, but the average, time averaged output compared with thermoelectricity actually is not that high. Okay, because there's always a temperature difference there. So continuous harvesting is the time average is higher. Okay, so if we use the wearable system, we need to look at a fiber-based one. The reason I already explained early on is comfort and also conform to the body. Here is comfort is one consideration. Conform the body with a very good contact with the human skin, and that is a must to provide thermal transfer properties. Otherwise, the device will not work properly. Therefore, we think fibrous structure like this can be three-dimensionally draped on even a sphere on human body in close contact would be ideal for this application. For making this, we're looking at answer the same question. If we have a material, we have a structure, and we have operation condition, what kind of optimized sets of parameter would be better for design? We provide a design basis, engineering design basis, understanding the process. Okay, so we do a modeling, and then we start designing our devices. For instance, we have one devices, is we call sandwiched flexible thermoelectric generators. We have made a new composite thermoelectrical material with very good performance properties. Then we make into little chips and then sandwich them between two flexible films and electrodes connected. And outside we also have the heat sink fabric. That is copper fabric made of very fine copper fibers. Okay, and then this is a photo of as-made devices, and this without the couple. Okay, and then we generate a power output. When temperature difference is 42 K, and you can see with the thermal sink, the output can go to around 9 milliwatts from this smaller device. And then power density is also pretty good. And this probably can utilize for some low-grade heat harvesting. However, if the temperature difference is small, like today in Hong Kong, we got a 37 degree and 36 degree, human body is 36. And then difference is 0, right? So we still need to look at a lower part and improve on those. Now, the output of this thermal generator is 32% of its theoretical upper limit. Okay, and in theory, it should produce something like 30 milliwatts, and still not yet, 1/3 of it. So we still have a space to improve. Okay, now we have all the devices, so I give you some examples and how my time goes. Am I right? Okay, or beyond time? Okay.
It's fine. You can go ahead. No
okay.
problem.
Okay. Thank you. And when we have all these devices, one difficulties we're facing is how can we put them into a system? And in a system, not only have sensors, have actuators, and you must have a brain, a CPU, and also wireless module, and a power supply, and so on. A lot of things, right? So we must have a system integration that can get everybody together in a form of wearable form. Ideally, it's a fibrous form because the comfort and the real-time measurement and action, right? So we look at a number of technologies available, and we think the fibrous structure probably is one of the good platform for us to develop wearable connections. Okay, so what we did is we look at a number of fibrous structure. Textile is one of them. Paper is another one. But the normal paper used for writing is not good because they disintegrated in water and very easy to tear off. We need to look at special papers. And these papers, we choose a number of them. Here is one of them, is a polyimide paper. Okay, and this is how it looks under microscope. Okay, and now start from this paper, and we coated, plated metals and nickel and copper in these two cases, and then we made into a coated conductive membrane. Okay, and this membrane can be, of course, can be made into circuit board. Okay, and then after this we can put a different microelectronic devices and also our devices on them, and then put a encapsulated with another layer of polymers. Okay, so to start with, we ask ourselves whether this process can be robustic, because for wearable must be able to be clean and also deform mechanically for many, many cycles. So this is one of the work we just finished. So when the whole thing is made, we put them into tensile test, okay? And the green one here is this finished, packaged circuit, what we call PMP, okay? And you can see the strength of the paper is not that high, and after finish, it more than double its strength, okay? In abrasion, if without the treatment, without the encapsulation, and they finished about several rubbers in abrasion resistance. So that is just not acceptable. But after encapsulation, it can go to 5,000 cycle of 50,000 cycle, which actually passed the most textile test. And so they can be used for the wearable application. And then what about the bending? And they can bend and up to 10,000 cycles. And there are some changes in the electrical resistance. Okay, and these bending, but they are much lower than the others. Okay, this is about the conductive tracks. And what about the washability? And they have excellent washability up to 50%, 50 machine washing cycles. They still get very good, close no change, okay, in the resistance. So that is a robustic. And then we make them into one-dimensional circuit. And to illustrate the effect, we put some LED because you can see without a measurement. The LED is in one kind of one-dimensional shape, and then we do in the paper circuitry, and then we put them into torture chamber, like a seawater, and put them into boiling water, put them into ice water, and they all work. And it can go to many thousands hours, okay, and still it's working. Bending cycles, and this is some illustration of the application doing some fun. So this circuitry technology, we can make into one-dimensional and two-dimensional electrical connections and easily put them into textile structure, and can be washed and can be worn without seeing them. And another, of course, roots is trying to pack everything together. If we can make thin, very flexible devices, we can stack them together in three-dimensional electronics format. For instance, this diagram, we have stack microelectronic chips with memories and also some flexible devices like capacitors and supercapacitors. We put them together in this kind of monolithic integration format. And we can save time and also can be made into quite a small and a rigorous package. Okay, they can be put into wearable system as an accessory. Now, this is some example we made, and we have integrated supercapacitor with LED and also controlling circuitry in one devices. Now, some of the technology we developed, investigated and developed has been commercialized. One of them is under title called Soft Sector. It's a fabric sensing technology. The products made are like this for monitoring respiration, monitoring human sex activity and sports, and for shoe, insole for the shoe, sports shoe, and other shoes. Okay, and now when we put them into application, there are a lot of other things like For sports, one example we have is to monitoring muscle contractions during active sport training. And we must do hardware, and then we have to do modeling and establish the relationship between the measured sensor, measured strength signal, and with muscle expansion, and trying to predict how much mechanical power, in this particular case, torque, can be generated by human muscle contraction. Okay, with that, I'd like to conclude, and also thanks the funding body and also my group. And these are the people who made this work possible. And I'd like to acknowledge their contribution. Thank you very much.